Hey, calculus. This is the worked out notes here for the second part of section 4.6 about related rates. So here's a few more types of problems that we'll progress through. Just kind of as a summary here, we've looked at related rates in terms of linears, where we're talking about just straight paths when we need distances or perimeters. We've talked about related rates when it comes to area problems, and we've also looked a little bit about related rates when it comes to three-dimensional figures. Now what we're going to do is we're going to kind of do a little bit more of a scenario that might require a little bit more than just the surface area or volume formula. All right, so let's see what we got here. First example, we've got an airplane. Airplane's flying at an elevation of 6 miles, and it's got a flight path that will take it directly over a radar tracking station. S represents the distance measured in miles between the radar station and the plane. If that S value, that distance, is going to be decreasing at a rate of 400 miles per hour when specifically the distance is 10 miles. I want to know how fast is this plane traveling, the velocity of the plane. Right. So in this situation, things might be a little bit more complex, a little bit more challenging to work with. So definitely want to use some type of picture or diagram to help you out. All right. So all the way up in the air, you got this airplane right here that's flying. Um, you got the wings of the airplane. Really bad drawing right there, but that's what we got. That's our jet. That's our plane flying up in the air, and we know that it's flying way up there at an elevation of 6 miles. So we're 6 miles off the ground right there, and we know somewhere overhead is um, is the fact that it's going to be kind of passing over this radar station, whatever that looks like. I don't know, some type of radar station, and it says it's going to fly directly overhead. So it's on a path that it's going to fly directly overhead. S is going to represent the distance measured in miles between the radar station and the plane. And S is decreasing at a rate of 400 miles per hour when S is 10. All right. So when it is when this value is directly overhead, we'd say that's 6 miles, 6 miles off the ground from the radar station. All right, but we don't necessarily know how far away it is. All right, so we'll say that the plane is maybe this distance over here. We'll call that x miles away. And then the other thing is this distance that the plane truly is from the radar station. We're going to call that s. My s's tend to look like 5, so I try to make that look a little bit more like an s right there. All right. Now the other thing that I could do is I could say the height. I'm going to call that maybe y right there. Okay. So I've got my setup right there to kind of help me out. I've got S, which is technically what S is. If you were a little confused by what S was, let S represent the distance between the radar station and the plane. All right, so that's what we got right there. And the reason that I say the plane is before the radar station, not on top of it, not after it, is it says it's on a path that it will go directly over it. Not there yet, but it's headed towards that. That's why I made the plane a little bit before we got to the radar station. All right, all right. So let's see what we can do right here. We have a couple things that we have. We have ds/dt. We have the change of the distance that the plane is with the radar station compared to the change of time, which is negative 400 miles per hour. Notice I say negative because it's decreasing. Okay, so we also have a specific s value. We have the specific s value, which is equal to 10 miles. What we're trying to find, what we're trying to find is it says to find the velocity of the plane. Well, that's the forward part that we got, not the up and down part, but the forward part. So that's x. So that's the distance right there. So we're trying to find dx dt, the change of the distance of x, the horizontal distance, which would be your velocity with respect to your time. Okay, so couple other things that we might need. I see a right triangle right here. So what I would do is I would use Pythagorean theorem. So I would say, all right, we've got x squared plus y squared is equal to s squared. Okay, and I can take that Pythagorean theorem and I can take the derivative of that. So the derivative of x squared is going to be 2x, and then derivative of y squared, well, that's going to be 2y dy dt. And then I'm going to set that equal to s squared. The derivative of s squared, well, it's going to be 2s ds dt. Fantastic. Okay, all right. So that's some of the information that I have. That's some of the information that I can use. And a couple things here. You see there's a 2, there's a 2, there's a 2. I can divide both sides by 2. And the 2's will drop out. The 2's will drop out. So I don't really need the 2's anymore. So I just have x dx dt plus y dy dt equals s ds dt. So the 2's are just kind of garbage right there altogether. They all drop out, which is pretty nice. It's less work that you got to do. All right. Remember, I'm trying to find dx dt. I'm trying to find this dx dt. So maybe get everything that's not dx dt over the other side. So maybe subtract this y dy dt and divide it through by x. So if I do that, that would say dx dt is equal to s ds dt minus y dy dt. Notice I subtracted the y dy dt, and then I'm going to divide it by dx dt. All right, so divide that. Oh, I'm sorry, not divided by dx dt. Divided by x. We're solving for dx dt. Sorry about that. All right, you guys would have caught that. So from here, actually substitute in what you have. Substitute in what you can do to try to solve it for dx dt. So s, the specific s value is 10. So I can substitute a 10. ds dt, the derivative of the distance that the plane is from the tower with respect to time, is negative 400. And I would go with miles per hour. I'm just going to hold off on units for now. Minus y. Well, the y is that fixed altitude, which is 6 miles, and then the dy dt. This one's kind of crazy. The dy dt, I don't have it, but is the plane really changing at all, going higher or going lower in this situation? No, it's flying at a steady path right there. So the change in the altitude with respect to time is actually 0. All right, so the derivative of 6, because it stays constant, is 0. Okay, and I want to divide all of this through by x, the specific x value. All right, and that specific x value is something that I don't quite have right now, but I can figure that out. All right, and if you want to try to figure out what that is, well, we'll go to your right triangle right there. Go to your right angle, your right triangle right there, and I'm just going to kind of do a little side note over here. Here's my right triangle. There it is. There's x. Here's 6. And I also know that the s value is 10. So here's 10. So I can use Pythagorean theorem to figure out what x is. So 10 squared is 100, 6 squared is 36. Subtract those two, and you get 64. Square root of that says x has to equal 8. So you can kind of solve for x right there, which is 8. Substitute 8 in the bottom. All right, I can calculate all this all out, and I'll end up with a negative 500 miles per hour. Now, if you might be wondering, wait, this says what's the velocity of plane, and it says negative 500 miles per hour. What does that mean? Well, that means we're going towards whatever unit we're calculating from. So if it were positive 500 miles per hour, it would mean we were going away from that. So negative 500 means we're coming in closer to whatever point of reference we have. So that's what I mean, 500 miles per hour towards that particular place rather than away. Okay, all right, let's try another one here. How about a boat speed? The boat pulled by a winch on a dock, and the winch 12 feet above the deck of the boat. The winch pulls the rope at 4 feet per second. Find the speed of the boat when 13 feet of rope is let out. What happens to the speed of the boat as it gets closer and closer to the dock? Okay, all right. So let's see what we got here. Again, a little picture might help you out. You got a boat. There's my boat. Great. And you've got a dock kind of over here on the side of it. And there's a winch that's kind of 12 feet above the deck. So I know that I don't even know how to draw a winch. So I'm just going to put a little line right there. That's going to be 12 feet above the deck of the boat. All right, so I could maybe kind of draw out another side. Oh, look, I got a right angle, and then I know that this is kind of the path that I'm going to be going up here. All right, so I've got 12 on one side. I don't know the other side. I'll just call that x because I'm not really sure what that is. And then the other side, the hypotenuse here, is going to be the angle that we're going to get pulled out of the water right there. So I might just call that S again, kind of like from before, just to kind of stay consistent right there. Specifically, it says the winch 12 feet. So I could maybe go with the Y value is 12, but I've got that in my picture right there. I also have the fact that ds dt, all right, the derivative s with respect to time, the rate in which this is being pulled at is at 4 feet per second. But remember, I'm going out of the water. I'm going closer to the winch, not further away. So I would go with a negative 4 feet per second right there. All right. And then I'm specifically looking when S is equal to 13 feet, when there's 13 feet of rope let out. What do I want to try to figure out? Find the speed of the boat. So I'm trying to figure out, find dx dt. Find dx dt right there. All right, so if that's what I need, I want to try to find dx dt. Something that we could do right from the start is we could use that Pythagorean theorem to try to figure out, well, what's the third side of the angle going to be? If triangle, if that's 12, we know the s value is 13. We got 13 squared minus 12 squared is going to be a 25, square root of 25, and you end up with 5. So that's the other thing. We can say, hey, x is equal to 5 feet to help us out when we go through and calculate this. All right, this is going to be another Pythagorean theorem problem. So I can say s squared is equal to 12 squared, or in this case, why don't we use the variables right there? 12 will equal y. So that would be y squared plus x squared. All right, okay, so take the derivative then. Take the derivative right there. So s squared's derivative, that's going to be 2s ds dt. Y squared is going to be 2y dy dt. And then x squared will be 2x dx dt. Super, okay. All right. And then hey, we got all the 2's. Let's drop those 2's out. All right, remember, you're trying to solve for dx dt. So we want to solve this for dx dt. So maybe we take s ds dt minus y dy dt, and we want to divide it all through by x, and that'll equal dx dt. And then we can substitute in. So we can substitute in everything that we have. The s value for this situation is 13. All right, the ds dt is negative 4. Minus the y value, that's going to be a 12. And then the dy dt, that's going to be the height of the winch. That's not moving. That's not changing. So I'm going to keep that as 0. And then divide that through by the specific x value. We use the Pythagorean theorem for that, and we ended up with a 5 right there. Okay, so we clean all that up. 13 times by a negative 4. 12 times 0, that's all gone. So 13 times by negative 4, all divided by 5. That's going to give me a negative 10.4 feet per second. So negative 10.4 feet per second. So basically what happens here is the speed of the boat is 10.4 feet per second, but it's getting closer and closer to the dock right there. All right, so that's what I mean by that negative right there. Super, okay. Last one that we'll look at in this particular round, a highway chase. We got a police cruiser approaching a right angle intersection from the north, is chasing a speeding car that has turned the corner and is now moving straight east. When the cruiser is 0.6 of a mile north of the intersection, the car is 0.8 of a mile east. The police determine with the radar that the distance between them and the car is increasing at 20 miles per hour. Okay. If the cruiser is moving 60 miles per hour at the instant of measurement, what's the speed of the car? All right, so a lot of situation, a lot of things going on here. Right-angled intersection, that's the key on this one. So a right-angled intersection, so I'm just going to kind of draw out a right angle right there. Okay, right angle right there. And I know that the car is already moving east. It's already made that turn. It's moving east. So I know over here it's 0.8 of a mile away, 0.8. And then up here where the police cruiser is still 0.6 of a mile. So I could go with 0.6 north of that. So I might call this distance right here maybe a y, this distance over here an x, and then the distance between the two of them, the specific straight line distance between the two of them, we'll call that value s. All right. Okay, so that's all the information I have. There's a little bit more in the explanation that I could say, hey, we also know that ds dt, all right, the change of distance compared to time between the actual two vehicles is 20 miles per hour. All right. We also know that the specific x value is going to be a 0.8, and the specific y value is 0.6, and that's miles, and that's miles. Okay. Um, there's one more thing that we know, and that's that the cruiser is moving 60 miles per hour at the instant of measurement of the instant measurement. So the cruiser's over here at y, and it's going towards the intersection, not away. So I could say that dy dt, the speed of the cruiser, which is going towards the intersection, so towards the point of measurement is going to be a negative, whereas away is going to be positive, is going to be a negative 60 miles per hour. Okay, all right. What I'm trying to figure out, what you're trying to figure out, find the speed of the car. The speed of the car is going to be the x value, so find dx dt. All right, so again, it's going to be a Pythagorean theorem problem. So we can go with x squared plus y squared is equal to s squared. All right, take the derivative of that. That would be a 2x dx dt plus a 2y dy dt is equal to 2s ds dt. Again, you see a common theme. You can cross the 2's off. So you have x dx dt plus y dy dt is equal to s ds dt. All right. Notice what you're trying to find. You're trying to find dx dt. So we want to rearrange this formula for dx dt. So I can say dx dt is actually equal to s ds dt minus y dy dt, all divided by x. Kind of like that. Okay. All right. Fantastic. Now let's substitute in what we have. So we've got s, the specific s value. Specific s value. If you're trying to figure out what that is and you're not really sure, go back to the Pythagorean theorem. All right, go back to that right triangle, and we have 0.6, we have 0.8, and we have the unknown. So we can go with 0.6 squared plus 0.8 squared is equal to s squared. Oh, cool. That tells us that 0.36 plus 0.64 is 1. The square root of 1 is 1. So the s value is 1. So remember, you can always use that to find a little bit more information out. So it's 1 times by ds dt, 1 times by 20, minus y times by dy dt. Well, we've got y is a 0.6 and dy dt is a negative 60. Okay, divided by the specific x value, that's going to be 0.8. All right, we clean all this up a little bit, and we actually end up with a 56 divided by a 0.8, which turns out to be 70 miles per hour. All right, so that car is traveling 70 miles per hour. Our police cruiser is only going 60 miles per hour. We still have to make the turn and then catch up to them. Better hope we got some backup. All right. Anyway, that's all I got. I'll see you next time. Bye-bye.